All right, so last class we took a look at these practice problems, and these just come from the practice problem section of chapter 6. Really good practice problems here. We get a lot of practice with the different arrow pushing mechanisms that we discussed last class. What were they? They were the nucleophilic attack, right? The loss of a leaving group, a proton transfer, and then a rearrangement, a carbocation rearrangement. Well, let's start out by looking at question 6.37. Last class, we did question 6.38. And remember that we have 3 steps here, right? We have step 1, then we have step 2, and then we have step 3. So you kind of take each section, right? The first section, this would be a step, what I have in this red box here. The second step would be, the second step would be what's inside this blue box here. And then the third step, is going to be this step here, right? So you've got to be able to understand that, the first step is just going from the first compound to the second compound. So let's take a hard look at that. So I'll delete those. And we're just going to look at the transformation of the first compound to the second compound. And you can see that we've got hydroxide here. And you can see that we've formed a bond, haven't we, right? The negative charge on the hydroxide can't go away. It can't vanish or anything like that. That's impossible. But you see the hydroxide ends up here. Could anybody tell me what type of mechanism we're looking at here based on the 4 types of mechanisms that we looked at? Absolutely, Edwin. Yes, it's a nucleophilic attack, right? The hydroxide is acting as a nucleophile, and this carbon here that I'm going to highlight in red, this carbon is acting as our electrophilic center. So this is a nucleophilic attack. So we're going to draw a curved arrow like this. There's a big problem with this arrow if I was to just leave it like this, right? Then you would have a carbon with 5 bonds, and that's impossible. And you can see that this double bond isn't here. Where did it go? Well, we have to move that double bond over here. You can see that this double bond is not here either. That double bond, or the pair of electrons, has been moved between the carbon and the nitrogen that's outside of the ring. So I'm just drawing resonance here, aren't I? And then lastly, you see that this double bond is no longer there, but there's 3 lone pairs and a single bond on this oxygen to give it a negative charge. And so I'm going to have to push these electrons up here. All right, if you find it helpful to add all the lone pairs at the beginning, you can go ahead and do that. Sometimes I do, sometimes I don't, depending on the situation. But there you have it. Those are the curved arrows for our nucleophilic attack. Okay, and this is a mechanism that you'll look at in organic chemistry too, in terms of learning the reaction. However, using what we learned in chapter 6, we can draw the curved arrows that represent the flow of electrons for this nucleophilic attack. All right, let's take a look at the second step. The second step, you see that when it says negative here, right, what does that mean? It means that this is going away. So this would be a methane sulfonate is what you would call this thing that's going away. So can anybody describe this mechanism? Would this be the nucleophilic attack, rearrangement, loss of leaving group, proton transfer? And it's not a trick question, just a regular everyday question. Yeah, it's a loss of a leaving group, right? This is a loss of a leaving group, LLG. Remember that a leaving group would be the conjugate base of a strong acid. What would be the conjugate acid of CH3 SO3 minus? It would be what? If you add H plus to that, you'd get CH3 sorry, there we go. You end up with this, okay? SO4, which is a sulfonic acid. This is called methane sulfonic acid, but either way, it's a sulfonic acid. Sulfonic acid. And if you think about this, what's the difference between this molecule and sulfuric acid? Sulfuric acid just has a hydrogen here. So this is a very strong acid. So this is a very good leaving group, right? And the negative sign here, that means that it is leaving. So that's kind of a dead giveaway that it's the loss of a leaving group. Well, how do we remove or lose this part of the molecule here, the methane sulfonate or the sulfonate? Well, you can see that we end up with a nitro group in the end. Remember that in nitro, we have a nitrogen with 4 bonds. It's got a positive charge. We have 1 oxygen with a negative charge on it like this. So that tells me that if I'm going from this to the nitro, then I'm going to have to take one of the lone pairs on one of these oxygens and make a double bond, right? So I'm going to take a lone pair here and I would make a double bond like that. But if I do that, then I've exceeded the octet rule with respect to my nitrogen. It would be surrounded by 10 electrons. So I'm going to make this pi bond here by taking these electrons and moving them here. I'm going to make this pi bond by taking this pair of electrons and putting them here. And then to lose my leaving group, I simply do this like that. And there you have it. There's the loss of the leaving group. All right. And then the last one, could anybody tell me what type of mechanism is happening in the last, the last step? And it's not a, yeah, exactly. Thanks, Mackenzie. It's a proton transfer, right? We're transferring a proton. Now, there's something I don't like about the way this is drawn, because I think he expects you to redraw everything in your textbook, because it's kind of difficult to draw a proton transfer when they don't explicitly show the bond from the oxygen to the hydrogen. That's kind of annoying. So let me just redraw the phenol down here. Okay, so I'm actually just going to redraw the whole compound. So there's your NO2, there's your oxygen, but I'm showing the bond to the hydrogen like that. Okay, so our proton transfer is going to go like what? The hydroxide is going to act as a base. It's going to take that proton. The pair of electrons between the oxygen and the hydrogen goes on the oxygen to give it 1, 2, 3, 4, 5, 6 electrons, and therefore we have a phenoxide. We have the oxygen with the negative charge. So we have our proton transfer. So overall, what did we have in this mechanism? We saw a nucleophilic attack, we had a loss of leaving group, and then in the last step, we had a proton transfer. Give me a thumbs up if you're feeling a little more confident. Even if you're thinking, I still need to study, I need to, review this and make sure I fully understand. But give me a thumbs up if you're feeling a little bit better. If you have a question, feel free to interrupt me. Yeah, I find that, curved arrows and recognizing steps of mechanisms, it's one of those things, it's one of the few times in organic chemistry, I think, that you can actually have like a bit of an aha moment where you're like, oh yeah, now I kind of get it. Right? It takes a little bit of investigating and looking at it in detail, right? What's cool about organic chemistry and what's so cool about chapter 6 is that you can look at a reaction like this one here. Look, you're starting it with this bicyclic molecule that's got a nitrogen in it. This is called an enamine. It's neither here nor there. But you see that you go through all these crazy steps, or interesting, and you end up with this molecule here. This is, in terms of the reaction, this is definitely beyond the scope of where we are at this point in our class. But in terms of the curved arrows, as long as they've provided us with each step, we can draw the curved arrows with our knowledge. Right? We can do that. Now, later on, what you're going to be able to do, towards the end of the class, is you'll be able to actually draw every step along the way yourself, and you're going to see that you'll develop those skills. But now we have all the intermediates drawn for us, and we're going to start by drawing some curved arrows. So let's see, we got the first step. We have our nitrogen, and then it's got a proton on it at the end. What kind of mechanism do you think is occurring here? It's not a trick question. Yeah, exactly. Mr. Dion should get a bumper sticker that says it's not a trick, right? It's not a trick question. It's a proton transfer, absolutely. Well, remember, you can't just go all willy-nilly, like I'll draw an arrow like that. That's incorrect, right? That's an incorrect arrow. If you were to start on the hydrogen and end up on a lone pair, there is nothing correct about that arrow whatsoever. Remember, the tail of an arrow has to start on a lone pair or a bond, and it has to end up on a nucleus like that. There we go. And then we're going to break this bond to give the oxygen a lone pair so that we form a water molecule. There we go. So there's our proton transfer. Moving right along to the next step. Well, something that is a recurring theme in organic chemistry, in case you didn't notice, and I'm going to review this with you, is that when you have an oxygen that's got a positive charge on it like this is a very powerful electrophile. And you see the same thing if you have a nitrogen that's got, we'll put H like this. If you have a nitrogen that has a positive charge on it like this, these carbons that I'll highlight in green, okay, are very powerful electrophiles. Okay. Not only because of induction, because the oxygen and the nitrogen are more electronegative than the carbon, but you could also draw a resonance structure for both of these where you'd have the positive charge on the carbon. So we see that arrangement right here. That tells us that this carbon here is extremely electrophilic. So could anybody tell me what type of mechanism is occurring here? And again, just give me your best shot. I knew you'd know. Absolutely. It's a nucleophilic attack, isn't it? Right? Water is behaving as a nucleophile. We don't think of water as being a strong nucleophile because it's not. It's actually a weak nucleophile. But when you have something like this that's such a great electrophile, yeah, it's going to do a nucleophilic attack. So let's draw the curved arrows. I'm just going to erase the carbon there. There we go. So there's our nucleophilic attack. But if we were to just leave that arrow like this, that's incorrect, because now we've exceeded the octet rule of that carbon. But you can see that this pi bond is going to break so that we can put the lone pair on the nitrogen. So we break that pi bond, and voila, we put the lone pair on the nitrogen like that. Moving right along, what's happening in the next step? You can see that we have an oxonium, right? We have an oxygen that has a proton on it. It's got a positive charge. It's not there, so this must be the transfer of a proton or a proton transfer. Who's going to take that proton? In case you didn't notice, right? Look, you've got hydronium, water, water, hydronium, right? Water, right? You see, it's got to be water or hydronium that's involved in each one of these, in a lot of these steps, I should say. So the proton transfer, the water is going to take a proton like this. It's going to regenerate hydronium when that happens. Okay, so let's look at the next step. That's this step right here. Now we have a nitrogen with a lone pair and 3 bonds, so it's uncharged. Over here we have a nitrogen with 4 bonds and no lone pairs. This must be another proton transfer. What's happening? The nitrogen is behaving as a base. Hydronium is an acid. So we're going to draw our curved arrows. I'll draw it like this. Okay, like that. There we go. So now we've protonated right here. Now, this is a more interesting step right here because we're going from this bicyclic structure to something that only has one cycle. My question to you is, could anybody tell me what type of mechanism is happening here? I'm sure you all tried it at home last night. When they say don't try this at home, you would say with OCHEM, do try this at home. Could anybody tell me what type of step is going on here? It's not a rearrangement because there's no carbocation. So in order to have a rearrangement, you've got to have a carbocation, and there's no carbocation here. This is actually a loss of a leaving group. Okay, this is a loss of a leaving group. Let me show you what I mean. Okay, you see how this part of the molecule here ends up over here? Well, that's because this pair of electrons is going to make a double bond, right? This double bond to the ring. And then this pair of electrons is going to end up on the nitrogen, right here. And that is actually behaving as a leaving group. You're losing that amine, okay, the amine portion. So that's a loss of a leaving group. All right, and then the last thing is just going to be a proton transfer. You have the protonated carbonyl. So the water molecule is going to come back in, take that proton, and you're left over with the carbonyl. And look where you end up. You end up in the last step, you took water and it grabbed a proton. That means that you end up with the product plus hydronium. I don't know what that is. Plus hydronium. Well, looky, you need hydronium to start all over again. Okay, so you could do this with a catalytic amount of acid. Anyhow, there we go. So that was some good practice. Those were some pretty quick answers by my students about, what type of mechanism is going on here. I didn't label this one proton transfer. So what have we got? We had a proton transfer, nucleophilic attack, another proton transfer, the loss of a leaving group, and finally a proton transfer. Let's take a look at question 6.47. This one I think is, it's not simple, but nothing is simple in organic chemistry. If it was, anybody off the street could do it. But I hope that what you're learning here is that this is just a matter of learning how to follow the patterns, right? Drawing the curved arrows that accomplish the following transformation. I'm going to go over this one a little quicker because I want to take a look at some other problems that are less complex than this one. But you notice that we're losing nitrogen into gas, right? This is nitrogen. You can put the lone pairs in here, right? You lose nitrogen, and you also lose chloride. So somehow we've got to lose this, and we've got to lose this. Well, if you take a look at what's happening in the very first step, if I zoom in on that a little bit, what the heck is happening here? Well, hydroxide is a strong base, and there's no nucleophilic attack occurring, right? But you see that this proton is missing. It's not here. So that means that the hydroxide must be behaving as a base and taking that proton. Well, where does this pair of electrons go? You can see that there's a double bond here, so I could take that pair of electrons and put them here. Then I see that this pair of electrons makes this pi bond, like that. And then I'm going to break this pair of electrons to give the oxygen 3 lone pairs and a -1 charge, like that. So it's a total of 4 curved arrows for this one proton transfer. Now what's happening over here in the next step, all right, what's happening here? This is where we have to end up losing the nitrogen, the chloride, and we're also making a carbonyl. So in order to make that carbonyl, okay, and we're also breaking the ring open, I'm going to take a pair of electrons from here and I'm going to make a double bond. Well, the problem with that is if I just made that double bond, then I've got 5 bonds to my carbon. I can't do that. So I'm going to have to break this bond, and that's where my triple bond comes from, right? I'm making a triple bond here. Well, again, that would break the octet rule for this carbon. So I'm going to break this bond and make my triple bond between my 2 nitrogens, right? Okay. Well, then again, that would exceed the octet rule of the nitrogen. So what happens is chloride is going to leave, and chloride is a good leaving group. It's the conjugate base of HCl, like that. And so this is also a loss of a leaving group. You're actually losing 2 leaving groups in this particular situation. I'm going to ask you guys, did anybody try question 6.50? Anybody give this one a try? Okay. Well, if nobody tried this one, I'm just going to go over it really quickly. You can see that in the first step, the base is or the hydroxide rather is actually acting as a nucleophile because we have an electrophilic carbon right here. And you can see that the hydroxide is actually attached to that carbon. So the first step is going to be a nucleophilic attack, where the hydroxide is going to attack here. And we make this alkoxide, like that. In the next step, we have a rearrangement. It's not a carbocation rearrangement. It's kind of a complicated rearrangement of sorts. I guess it could be viewed as a loss of leaving group, maybe more accurately, because you're losing an acid. But anyhow, what's happening in the next step is that this alkoxide here needs to take a proton, and you can see that this proton is gone. So it's actually taking this proton in this, which is a proton transfer, and then you're going to rearrange like this to form this compound, and then you lose hydroxide like that. And then in the very last step, it's just a proton transfer where you take this proton like that. Anyhow, if nobody did that one, we'll move on from there. And I wanted to take a look at a question from the back of the book, which is, I want to first take a look at one of the questions in 6.28. Just give me a second here. There's some space here. Okay, let's take a look at 6.28b. So this is 6.8b. So we have these 3 compounds. This one, and then we have this one. You can see they're all isomers, and they're all different carbocations. Like that. And if I call this one, if I call them A, B, and C. Could anybody tell me which one of these would be the most stable carbocation? Yeah, it's going to be A, would be the most stable. Can anybody tell me why? Because if you just take a look at A at first glance, I mean, it's a secondary carbocation, but so is B. B is also secondary. Why would A be more stable? Why would A be a more stable carbocation? Yeah, it can participate in resonance. Exactly. Because it's secondary and it's benzylic. It's in the benzylic position. Remember that when you have an aromatic ring like this, okay, this position, okay, one carbon away, okay, it doesn't matter what's here, it could be anything, okay, but this position is called the benzylic position. So since it's secondary and it's benzylic, like Bruna said, it can participate in resonance. So if we were to draw, you know, all the pi bonds in here, you should be able to draw all the resonance structures for that compound. So there you go. It's secondary benzylic. Even though this is secondary, since it is benzylic and can participate in resonance or has resonance contributors, it is going to be more stable than the others. And then which one would be the least stable? Can anybody tell me which one would be the least stable? There's one that's a really bad one. Yeah, exactly. This is going to be the least stable, right? Least stable. Why? Because it, because it is primary. Okay, it's a primary carbocation, so it is the least stable of all the carbocations. All right. I also wanted to take a look at question 6.30a. So this is 6.30a, and I'll draw this compound out. So okay, and what it's asking us in here, it says for the compound, this compound exhibits two electrophilic centers. Identify both of the centers in each of the compound. So if I number the carbons, and this isn't the neatest structure, is it? There. Well, it's good enough. All right. If I number the carbons in this aldehyde, it's carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. Could anybody tell me which carbons, and again, there's two of them, would be electrophilic? I'm looking for an electrophilic center. Number one, for sure, right, Benjamin? Absolutely. Couldn't agree more. Okay, everybody's saying number one, and I totally agree with you, right? Because we have an inductive effect, right? Because of the carbonyl, right? The oxygen is, delta minus, and the carbon is going to be delta plus, right? Because of the inductive effect. So absolutely, yes, carbon 1 is going to be electrophilic. Now, what about another one? So I see somebody saying carbon number 4. Okay. Any other ideas besides carbon number 4? Any other votes? So what you might want to do here is you might want to draw some resonance structures. So let's take a look. What would happen if we were to draw a resonance structure like this? Okay, well, let's see what we would end up with. I guess I'll just copy and paste the molecule. That might be faster. So just give me a second here. And you can probably draw these resonance structures faster than me with a pencil. But once we do that, we would end up with what? We'd end up with something that looks like this, where we have the negative charge on our oxygen, we have a positive charge on our carbon. So that clearly shows that carbon number 1 is electrophilic. But is there another resonance structure we can draw? For sure there is, right? We could also draw a resonance structure, and I'm kind of going sideways here. I'm not going, there's no rhyme or reason to my direction here. But anyhow, if I go like this and I move that pi bond over because I have an allylic carbocation here, and this again goes all the way back to chapter 2, well, what's that going to look like? So let's see here. Paste this right here like that, and let's draw what that would look like. So now we've got our double bond here. We've got our negative charge on our oxygen, and now our positive charge is on carbon number 3. And so there's no other resonance contributors that we can draw. Therefore, the answer is going to be, I'll highlight them in green, it's going to be carbon number 1 and carbon number 3. So C1 and C3 would be the two electrophilic centers. In fact, we look at, this is called an enone, sometimes it's called an enone, or you can call it an alpha beta unsaturated ketone. Anyhow, what you're going to see is that in organic chemistry too, we do an entire chapter where we look at the chemistry of these guys, and we see how a nucleophile can attack a carbon 3, or it can attack the carbonyl carbon, depending on the situation. Anyhow, there we go. So we've identified the two electrophilic centers. And if you look at question 6.30b, it's in the exact same vein, okay? It's the exact same type of question. So I'll skip that one for now. Let's take a look at 6.41. I want to isolate some of the problems in there. So 6.41, and the question is, will it undergo rearrangement? Okay, so if I write down A, which is this carbocation, will this undergo rearrangement? A. Could anybody tell me with this, yes or no? Yes, it'll rearrange. No, it's just going to stay the way it is. So I'm looking at 6.41A. Will this undergo rearrangement? Yeah, I agree. I think it's going to undergo a rearrangement. All right, we have a secondary carbocation. So this is secondary. If we look at the carbons next door, you look at this carbon. If you were to do a hydride shift from that carbon, let's say, so let's draw in one of the hydrogens. If you were to do a hydride shift like that, you'd end up with what? You'd end up with this guy, okay? And now you'd have the carbocation here. That doesn't help you at all. It's still secondary, so you haven't done anything useful at all. It's not further stabilized. Remember, carbocation rearrangements are going to occur if you end up with something more stable. Well, I'm going to go to the next door neighbor, which is this carbon, which has two methyl groups on it. If I was to do a hydride shift with one of these over here, what do I end up with then? I get something that looks like this. Now I have a methyl group here and I have a methyl group here. I've filled out the octet of this one, but this carbon is electron deficient now, and so it's got a positive charge, but I've gone from a secondary carbocation to a tertiary carbocation, and so the answer is yes. This rearrangement will occur because we end up with something more stable. Let's take a look at B. Could anybody just answer B? Tell me yes or no. Yes, it's going to rearrange. Nah, it's going to stay the way it is. So I got a vote for a no. Any other votes? Any other votes for B? Well, let's take a look at B then. So if we take a look at B, there's two beta carbons, right? There's this one and there's this one. If I was to shift this proton over here, if I was to do a hydride shift like this, what would I end up with? I'd end up with this molecule, which doesn't help me at all. I go from a secondary carbocation to a secondary. However, if I was to try to do a hydride shift from this proton into here, then what do I get? I go from a secondary carbocation to a tertiary carbocation. So I go from a secondary to a tertiary carbocation. And so in this case, yes, it will undergo a rearrangement. It will undergo a rearrangement. What about C is kind of will not undergo a rearrangement? Let's go to D. Let's try D. We have this, okay, and we have a carbocation over here. Will this undergo a rearrangement? This carbocation. Anybody have a feeling? I say that this one would, right? I say absolutely it would. I say it would undergo a hydride shift. Right, if we were to shift one of these hydrogens, I would go from a secondary carbocation. If I was to shift this over, what do I end up with? I end up with this, my double bonds here, but now I have the positive charge here. Now I've got a secondary allylic carbocation. So this is secondary allylic, right? This one is resonance stabilized. I mean, you can draw the resonance contributor. like this. Okay. So you could take the time to draw that out if you want. But there you go. You go from something that isn't resonance stabilized to something that is resonance stabilized. Let's try one more. What about 6.41F? I'm going to draw the compound out for you here. Sorry, yeah, 6.41F is the one I wanted to try. We have a carbocation here, and we have all this spinach over here. What about this one? Would this one undergo a carbocation rearrangement? Anybody have a feeling about this one? I have a secondary carbocation right here. Okay, I'm getting some votes. We've only got one vote so far. Okay, I got a no and a yes. We got a split classroom, so let's take a look. Well, if I was to do a hydride shift from this carbon here, I'm not even going to draw it. I'd end up with a primary carbocation, so that's not going to help us. All right, if I was to shift this methyl group over here, which let's just draw it for experimental sake, okay? Then I'd end up with this, and it'd have my positive charge here, so I'd go from a secondary to a secondary. That also doesn't help us, so let me erase all that. But what if I did a hydride shift? If I took this hydrogen, let me just erase my secondary. If I was to take this hydrogen and shift it over like this, then what do I end up with? Well, let's draw it out here. I end up with a positive charge over here. So I go from a secondary carbocation to a tertiary carbocation. And so the answer is yes, it will undergo a carbocation rearrangement. All right. Does that help a little bit in recognizing when something is going to undergo a carbocation rearrangement? All right, cool. Good. Yeah, you have to kind of practice looking at those. See, I'm looking through the... Are there any questions in particular from the back of the book? There was none other ones that I had picked out. Make sure that you do a problem like... make sure you do at least a couple practice problems that involve bond enthalpies, because what I'll give you for the next quiz, for quiz 6, is I'll give you a table of bond enthalpies as a handout that you can bring into the quiz with you, and then you'll have to use it to calculate the delta H of a reaction. So there's one question I'm telling you that I will ask. I always ask that. You know, we always ask our students that just to make sure that they can answer a question about bond enthalpies. And, you know, what else is going to be the type of things that I would ask, right? I'm going to ask about equilibrium constants and rate constants and, you know, change in entropy, change in enthalpy gives free energy. The dependence of delta G on temperature, we'll talk about that, or we've already talked about that. So, yeah, those are the kinds of things. You notice that there isn't a ton of practice problems at the end of chapter 6. So make sure you do all the practice problems that I've suggested from the chapter. Make sure you give every single one of them the old college try. And of course, if you have any questions about any of them, feel free to reach out to me by email. And if you ever want to meet with me on Microsoft Teams, just let me know. Just say I'd like to speak to you, you know, one-on-one. I want to see your face, see your lips moving, you know, explaining something or whatever. And I have no problem doing that. All right. Here we go.